Today it's gonna be chapter 8. Yeah, this chapter is also very, very important because this topic is really, really important in practice. That is Markov chains and random walks. Okay, what is Markov chain? Markov chain is a system described as follows. So we have 4 states, 4 different states, and there are transitions between states. So, for example, from 1 to 2. Okay, so there are several possible transitions from state to state. And from state 1, it's possible to go to state 2, and also possible to go to state 4. And this is 1/4, and I'm sorry, this is 1/4, and this is 1/1/2. Yeah. So each transition has a probability. Each transition is a probability. Okay? Okay. Each transition has a probability. For example, from state 1, the system goes to state 2 with probability 1/4, to go to state 4 with probability 1/4 again, and the system can go to state 3 with probability 1/2. That's quite easy. So Markov chain is a system such that each transition just depends on the current state. No other thing. It solely depends on the current state. So if you are now in state 4, then your next state is 1 or 2. Depending on the states. Depending on the probability. Okay. This is not very important, but we usually assume that the system is strongly connected. Strongly connected and aperiodic. Not periodic. Okay. What do I mean by strongly connected? Strongly connected it's pretty easy. Strongly connected means you can move from any state to any state. You can move from any state to any state. So, for example, this system, this Markov chain, is not strongly connected. Okay? Because from this state, you cannot go to this state. So this is not strongly connected. Okay? Strongly connected means you can go from any state to any state. But this is not strongly connected. What is aperiodic? For example, think of this system. For example, think of this state. Oh, the probability is not very important. Maybe all 1/2. Maybe all 1/2. The probability is not very important. This system is periodic. Periodic, meaning, suppose that you are here at time 0. Then at time 1, which state will you be? Will you be in? You will be this or this, right? Time 1, you know, so you go from here to here or here. So time 1, you should be here or here. What is time 2? What time 2? Maybe you can go back here or you can go here. That means you'll be here or here, but never in those two states, right? So that means in the even time step, you'll be here or here. The odd time step, you'll be here or here. So this is what we call periodic. Periodic. Okay? So aperiodic means no, we don't assume this kind of periodic state transitions. Okay. So we usually assume the system is strongly connected and aperiodic. Good. The system is described by a transition matrix. Like this. It's a transition matrix for this Markov chain. That means from state 1, it can go to state 2 with probability 1/4, also to state 3 with probability 1/2, and so on and so forth. The sum of each row must be 1.0. Okay, the sum of each row is 1, again 1, 1, 1. Okay? So this is a transition matrix. It's pretty easy. Oh, by the way, I forget to say something about its importance of Markov chain. And you know, this appears in many different situations in practice. But probably nowadays, the most important example is page rank. Page rank. You should know page rank in Google. Okay? Google, page rank in Google is exactly using this Markov chain. Okay? So if you're interested, why don't you visit some web pages explaining a page rank of Google? Then no, you can see, this is it. Yeah, exactly Markov chain. Okay. This is a transition matrix. And suppose that the current Okay. So suppose that the current distribution is 1/3, 1/2, 1/6, and 0. That means we are assuming, we are assuming in that we are in state 1 with probability 1/3, state 2 in 1/2, state 3 in 1/6, and state 4 with 0 probability. So this is, suppose that this is the current distribution. Then next distribution then the next distribution is easily calculated as follows. Namely, okay? This is a pretty easy calculation using the transition matrix. So the current distribution is here, 1/3 to 1/2, 1/6, and 0. Then the next distribution is that distribution. Okay. Now suppose that we repeat this. This is the next, this is a distribution in step 2. Okay, this is a distribution in time step 1, then this time step 2. Then what is time step 3? Of course, that we can do exactly the same thing. So by multiplying the transition matrix here. So let's repeat. Let's repeat that. Then we can get a stationary distribution. Meaning, we repeat this calculation. Step 3, step 4, step 5, step 6, maybe step 100 or step even 1000. Then, interestingly, the distribution is approaching to the unique distribution. That is called stationary distribution. It is known that the system is going to some fixed distribution, converges to some fixed distribution. That is called stationary distribution. We usually use this pi bar for this stationary distribution. And this is exactly a page rank. So if you think that the web is a big graph like that, web is a complete in a big graph, just looks like that. And then from this web page to that web page, we have a distribution. We have a transition probability. Okay, so the exact is a Markov chain. And the stationary distribution means, each web page, how popular each web page is. That is stationary distribution. The stationary distribution is high in the state, then that state is popular. Okay? So this is exactly a page rank. Okay. The stationary distribution, of course, satisfies this equation because, it's exactly like this. Like this. But this, the current distribution and the next distribution is the same. Current distribution and next distribution is the same. That is the definition of a stationary distribution. Then, so we can use a system equation equations. For example, let's say x, y, this example, this is exactly that Markov chain. Then the system equation is something like x. X is equal to, multiplication like this. Then the next y. Y is equal to, like here. Okay, so okay. So we can obtain this system of equations. It's pretty easy to solve this equation. Then we have a unique solution. For example, in this case, stationary distribution is this. This is a stationary distribution for that Markov chain. So if you think that that is a web page, it's a really small web page, then the page rank of the state 1, web page 1, is 8 over 139. This the web page 1 is not very popular. The most popular web page is number 3. Why number 3? Maybe I don't know. It's receiving a lot of edges. So maybe, it's reasonable that this number 3 page is quite popular. Okay. So this is stationary distribution. Now, we have a definition, bit more definitions. Okay. We first define RIJT. RIJT. RIJT means it's a probability that the system goes from state I to J in exactly T steps. What does it mean? It's pretty easy. So for example, R132. R132 means the probability that the system goes from 1 to 3 in exactly 2 steps. Okay? How can go from 1 to 3 in 2 steps? One possibility is here. 1, 2 steps. And also 1, 2 steps. Okay? So what's the probability? The probability is 1/4 plus 1/6 equal. This is the probability. Why? Because in 2 steps, one root is here. The probability 1/4 times 1 is equal to 1/4. And the other possibility is like this. Then 1/2 times 1/3 is 1/6. So the probability is this, 5 over 12. Now the next definition . The next definition is Hij. Hij is the expected number of steps to go from state I to state J. For example, H 1, 3. Yeah, this is a little bit complicated. Hij is the expected number of steps to go from state I to j. So for example, h13 is the expected number of steps that the system goes from 1 to 3. 1 to 3. Okay? So for example, the system you can go from 1 to 3 in one step. In one step with probability 1/2. That means 1 times 1/2. You can also go from here to here in two steps, like this and this. The probability is here. The probability here. You can also go from here to here in three steps. For example, this is 3 steps. So 3 times 1/4 times 1 times 1/3. Plus several different possibilities. This and this. Okay? That is here. 1/2 times 1/3 squared. And what is this? 1/4, 1/5, 1/2. 1/4. 1/4. Yeah, 1/4, 1/5, and 1/2. That is also 3 steps. And also 1/4, 4/5. What's that? 1/4, 1/4. Oh yeah, 1/4, 4/5, and 1. Yeah. Oh, this is the 3 steps, and maybe 4 steps, 5 steps. This is continues forever. This is not so this is not so easy. Not so easy to calculate. Maybe as an example is H33. H33 is what? H33 is just from the expected number of steps. You can go from state 3 to state 3. So once you leave state 3, then can come back to state 3. How many steps do you need? That is H33. Okay? So what's H33 is it's a bit complicated to. Okay. So from 3 to 3, in one step with probability 1/3, 2 steps with probability 1/9, and 3 steps with 1/27. But for 3 steps, there are different possibilities. This is also 3 steps, and this is also 3 steps, and maybe 4 steps, 5 steps, 6 steps. It's again very difficult. However, yeah, this is difficult. This is difficult, but this is not very difficult because we have the following theorem. We have a following theorem. HII is quite easy. Oh, by the way, what is pi I bar? Pi I bar is a stationary distribution for state I. State I. Yeah, proof. Just a sketch. Okay. Just remember the example. The stationary distribution, the probability that you are in state 1 is 8 over 139. Here. Okay? In the stationary distribution, you will be in state 1, the probability with probability 8 over 139. This means okay. In the stationary distribution, you will be in state 1 with the probability 8 over 139 means you are in state 1 8 times out of 139 times. Okay? If you are in the stationary distribution, you will be state 1 with the probability 1 over 139. That means out of 139 steps, just you count 139 steps, then probably you will be in state 1 8 times, right? That's the probability 8 over 139. Okay? You just you just observe your state in 139 steps. Then probably you will be state 1 in 8 times. Okay, so now this is a stationary distribution. Okay, it's your starting point. Then after a long time, now you are in the stationary distribution. Now this is time step. Okay, time step. You just observing 139 time steps. Then you will be here in state 1. State 1, maybe state 2, maybe state 4, and here you're also state 1, and here you're state 1, and you're state 1, and state 1. So 8 times. This is what this means. If you look at 139 time steps, then you will be in state 1 in 8 times. Okay? Then what is average time steps between two ones? That is exactly 139 divided by 8. Okay? That's why we need these time steps to come back to state 1. So HII is easy to calculate because this time stationary distribution is easy to calculate. Okay, good. We are moving to the next topic, that is random walk. Next step. But random walk is just a special case. Just a special case of Markov chain. Because I made a mistake. I erased the previous system, but okay, no problem. 2, 3, 4, 5. Yeah, it looks like this. This time, the graph is not directed, undirected. This is not arrow, but just a simple edge. Okay. Okay. So this is a special case of Markov chain. That means we change okay. So just by changing this graph a little bit, then we can get a Markov chain. How can we do that? Just change a single edge by two arcs. And then the probability is all the same. Then you can get just Markov chain. So, I'm writing the probability this side and this side. So this side means the probability of this arrow, and that side the probability of that arrow. Okay? So then this is exactly a Markov chain. The important thing is the probability is all the same for the arcs. So this is 1/4. This is we have four edges, four arcs of this direction. So all the probability is all 1/4. Okay? So this is a random walk. So random walk is just a special case that if you are state 1 now, then you will go to state 2 or 3 or 4 or 5, equal probability. All equally likely. Okay? So this is a natural case, natural assumption in practice in many cases. Okay. Now we have a couple of theorems. The first theorem is very important. Pi I. Pi I is what? Pi I is a stationary distribution. Okay? Pi I is a stationary distribution. Of course, the stationary distribution can be calculated by solving state of equations, but you don't have to do so this time. It's much easier. It's much easier. In the stationary distribution, you will be in state I with this probability. With this probability. What is this probability? Okay. M is the number of edges. And di is the degree of node I, vertex I. Maybe we say vertex. So now it's quite easy. For example, what is pi I? Pi 1. What is pi 1? We have 1, 2, 3, 4, 5, 6 edges. Okay? I'm sorry, maybe 1, 2, 3, 4, 5, 6. Yes, 6 edges. And the degree of vertex 1 is 4. That means the probability that you will be in state 1 is 4 over 12. That means 1/3. So you don't have to solve the state of equations. Now it's pretty easy. It's pretty easy. What's the probability in state 2? State 2 is 2 over 12, 1/6. That is, just proportional to the degree, to the number of edges, attaching your state. It's pretty easy. Okay, let's prove. Remember that the system of equations has a unique solution. Of course, this probability can be obtained by solving that state of equations. Exactly that state of equations. And that equations has a unique solution. Therefore, okay, so instead of solving the equations, we just check that the given, the given probability, the probability given in the term just satisfies the system of equations. That's enough. Okay? Instead of solving the equations, we just check the probability just satisfied the system of equations. Okay, let's do that. Maybe I'll use an example. State 3, state 5. State 1, state 6. Okay? So suppose that state 3, node 3 has 3 edges. 3 edges to vertex 1, 5, and 6. Then so this is the state of equation. This is the state of equation. Okay? Pi 3 bar, your probability here is pi 1 bar multiplied this probability, 1 over d1. Okay? This is the probability 1 over d1. Okay? 1 over d1. Plus pi 5 bar, multiplied by 1 over d5, plus pi 6 bar, 1 over d6. This is equal due to the probability that is claimed in the theorem, is this pi 1 bar is d1 over 2m. Pi over 2, this claim, due to this claim, pi over 2 is d5 over 2m. Pi 6 is d6 over 2m. But this is exactly, this cancels. Exactly, those cancels. This is 3 over 2m is exactly d3, degree of 3 over 2m. So the claimed probability exactly satisfies the system of equation. Okay, that's fine. Great. So we are done. Now next theorem. HII is 2m over di. This is exactly mediate. This is this is immediate from the previous two theorems. For example, one theorem is here, HII is 1 over pi I bar, and pi I bar is exactly given in the theorem. That means HII is 2m over di. Okay, meaning, for example, in this system, how many steps do you need from 2 to 2? from starting 2 and coming back to 2. How many steps do you need? You need 12 over 2. 12 over 2 means 6. So from state 2 coming back to state 2, you need 6 steps on average. You need 6 steps on average. Right? From state 3 to state 3, you need 12 steps on average. Pretty easy. Pretty easy. Now, the next system theorem is important. Next theorem is important. Okay. This is pretty important. Suppose that you have two states, two nodes, U and V, such that there is an edge between them. Okay? You have a node, state, V, U and V, and there is an edge between them. Then HUV, that means from starting this U and coming back to no good. Starting from U and coming back to U, okay? You need at most 2m. Most 2m steps. This is a very important theorem. Very important theorem. Okay, proof. So think of something like U, like this. It's U and W, X, Y, Z. So suppose that node U has 4 edges. 4 edges, 2, X, Y, Z, and W. Now, U is equal to 2m over du due to the theorem. Due to the theorem, from U to U, you need these steps on average. And also, HUU can be written as follows. No, this is not W. This is V. Sorry. Also, HUU can be written as follows, like this. What is the expected number of steps? What is the expected number of steps from U to U, but the first move is U to V. is equal to first move to U to V needs 1 step plus H V U. Okay? H V U. This is the number of steps from U to U, but the first move is to V. Right? Okay? Just taking average. Just taking average. Just taking average. That is HUU. Okay? Once again. Now you are calculating number of steps from U to U. There are four possibilities. One possibility is first go to V and come back. Second possibility is first go to X and come back. So 4 different possibilities. The first possibility is, you need 1 step plus HVU. Okay? Just taking average. Of course, NU is equal to the neighbor of U is equal to X, Y, Z, V. Sorry. Okay. So that means it's pretty easy. From those 2 equations, you can obtain that this part is exactly equal to 2m because just divided by du cancels. Okay, so this part is exactly equal to 2m. So this value, of course, at most 2m, and this holds for any w. This holds for any w. If there is an edge between them. Why this is important? Because look at this graph. This is 0, -1, -2, -n. 1, 2, n. So we have 2n states. We have 2n vertices. Just a line. And due to the theorem, H0 minus R. H0 minus n at most 2n squared. Why? Because okay. This is a pretty easy implication of the theorem. From this state to this state, you need at most 2m by the theorem. From this state to this state to this state, you need at most 2m. In this case, I'm sorry, this is a little bit different. This is strange. We have 2n edges. Oh, I'm sorry. the foreign. Okay, sorry. Okay? So from this to this state to this state, we need at most foreign steps. Foreign steps. And from this state to this state, again, we need at most foreign steps. That means from this state to this state, you need at most foreign times n steps. And this is why this is important. Why this is important? You can think of a game. Between A and B. This is a game between person A and person B. The game is very simple. Just flip a coin. Flip a coin. Okay? A wins if the outcome is a head. B wins if the outcome is a tail. Okay? So exactly it's a fair game. Exactly probability 1/2, A wins, and with the probability 1/2, B wins. If A wins, oh sorry. If A wins, then, just B pay 100 yen to A. If B wins, then A pay 100 yen to B. Suppose that A and B have 1,000 yen per each. A has 1,000 yen and B has 1,000 yen. Then A or B bankrupts within 400 steps by the theorem. Exactly, in this time, this is a starting point. This is a starting point. Both people have 1,000 yen. If A wins, then the state changes to this. Okay, 100 yen. That means n is equal to 10. N is equal to 10, and that means H0 minus n is at most 400. That means average steps from here to here is 400. Also, from here to here is also 400. That means, with high probability, within 400 steps, A or B, just bankrupts. No money at all. No money left. It's exactly the same for, just when you play pachinko. Yeah? It's a very important theory in this kind of game. Yeah. Okay? So these further steps are maybe a little bit too much. Maybe a little bit too much. Maybe it's a good idea to do some experiments using your computer. Not just simulating this game. Then exactly A or B go to bankruptcy within some steps. Yeah, and the number of steps is of course important. The number of steps is of course important, and that is usually something like this. Something like this. Okay, that means from here to here, you need n steps. Then it's something like n squared. N squared. Always A wins. If A always wins, then it needs only 10 steps. But the same probability, then something like n square steps. That is very important. Yeah. Good. So this is very easy. When you play a game with a friend, then just calculate in your brain. In your brain. It's all. I always win, then he'll be bankrupt. He'll be bankrupt is maybe five steps. Then the game is fair. Then I need something like 25 steps. If I am lucky. Okay. Good. Now, let's remember the local search algorithms. 3SAT. Okay? X like this. Suppose that now this clause is 0. This clause is 0. Just remember, local search algorithm is just use a random assignment. Just use a random assignment. Then just look at the clause that is false right now. So for example, this clause is false. That means 0, 0, 0. Okay? So at least one of the three assignments is bad. At least one of them is bad. Maybe this is bad, or this is bad, or this is bad. So let's flip. Let's flip the value of the variable. Okay? Just randomly select one of the three variable and just flip its value. For example, flip this value to 1. Then, with probability 1/3, this selection is correct. You mean you can flip the right variable. Then this is exactly random walk. It's a random walk. And if you are right now, okay, that means right now means this number of variables are bad. This number of variables are bad. This is the final answer. And right now you are here. That means this number of variables have bad assignment. Now if you flip one variable, then you can go this direction with probability 1/3, and maybe you will be failed. You will be failing with this probability. Then just remember, you need something like 1.3342n steps. from the initial assignment to the goal. Okay, this is exponential. This is exponential. Very bad. Very bad. Okay? Completely different from that situation. From that, this is the distance is just n over 2. But from here to here, you need this number, this many steps on average. So that is exponential. Why? Because the probability is different. This is a very important point. That's a completely different. Probability is different. However, what about TUSAT? What about TUSAT? Then, by doing exactly the same argument, now suppose that you are here, then by flipping one variable, then you can go to this direction with 1/2, with probability 1/2, and this bad direction with probability 1/2. Exactly the same as that. Okay? Now the situation is completely different. How many steps do you need? By this theorem, by this example, you need only n square steps. N square steps. 3SAT and 2SAT is completely different. 2SAT is pretty easy. 3SAT is difficult. Okay, this is only by using our local search to solve those problems. But actually, in fact, there are several different algorithms to solve 2SAT in polynomial time. Actually, we don't need n square steps. We need linear steps. We actually need linear steps. So 2SAT is very easy. But 3SAT is NP complete. That means 3SAT is very difficult. Which, the difference between two problems can be described by this local search very well. The probability is different, then you need too many steps. The probability is the same, or just, you have n square steps, polynomial number of steps. Okay, so today, I gave you a basic idea of Markov chain and random walk. This is very, very important. It appears many different cases in practice in the real world. The best example is PageRank in Google search system. Okay, good. So we are done today, and also we are done in the course. Just remember what you learned, what you studied in this course. In this course, there are many interesting situations in today's contemporary algorithms. Now, what we are doing in design and analysis of algorithms is completely different from the previous studies. In the previous studies, maybe 20 years ago, when you go to algorithm course, then you are always studying something like sorting, searching, and something like the graph problems, the computation time, n square, n log n, or linear time. What you have learned is exactly those kind of things. But nowadays, our problems in design and analysis of algorithms completely different from the previous ones. Okay. I hope you can feel something from this course. Okay, and thank you very much for taking this course. And just remember that you need to submit your answer by the end of this month. Okay? Good. So have a very nice summer vacation season.